super happy to be here. I hope you still have a bit of energy after those 2 very, very packed days. Here we go. This is the kind of thing I want to use every day. I want to have like small little bricks that are very easy to assemble to build some nice stuff, some nice and complex stuff like this, right? I want to be able to play like that with my software. And I'm not really kidding, because this is how we teach kids to program these days. Oops, sorry, too fast. With environments like this. This is the Scratch environment from the MIT, teaching kids how to program by having all those blocks, forming more complex functions together. A bit like Lego. Unfortunately, my own environment sometimes doesn't really look like this. It's a lot more complex. There are more pieces, and I'm always worried if I touch this, is the ball still going to roll, and is the mouse can still be cut at the end or not? It's really difficult. So this is why today I want to talk to you about those bricks, those components, those modules that we use, or that we should use. And first of all, why it's important to think about them. Second, why it's hard to get this modularity we're after. And then, what can we do about this? What kind of tools do we have at our disposal to deal with this, okay? So, why do we care about modularity? Why is it something that's important, that should matter to us? Well, we should care about modularity because that's one of the primary tools we have for reducing complexity. It's very easy to build complex systems that are hard to understand, hard to evolve, and so on. And modularity is giving us tools to do this. And one first thing that it gives us is a way to isolate things, to make sure when you have failures in one place that it's not going to propagate everywhere. And this is not something that you find only in software systems. That's something you find in many other physical systems. Like in a tanker, for example. You don't put all the oil into the same big tank. You have actually several small tanks inside. So if there's one of them that spills, it's okay. It's not affecting the other ones. And it also gives you some very nice physical properties, because if you don't have all the oil into one big tank, when the sea is a bit rough, it minimizes the amounts of movements inside the boat. So that's the kind of properties we're also looking for our software, right? When there are issues, when there are evolutions, we want to absolutely minimize the impact on the rest of the system. So modularity really helps us with this. The next thing is understanding. Having a modular system really helps you understand your system. If you take a system like Windows 10, for example, it has something like 3.5 million files. So if you start reading those files one by one per minute, you will spend the next 20 days of your career just doing this. It's impossible to work like this on such a system. But fortunately, people still succeed in working on those systems because they get higher level views to get an understanding of what those things are doing. So if you compare the picture of this engine compared to the previous one, this one is more understandable. You can see there's a cold section, a hot section, and then you can dive in. You can drill in the system and understand what each part is more precisely doing. The high-level view will not explain everything. There are probably many very small details will be still very relevant, very important, but at least you will get a rough understanding of what's going on because you have those modules. The next thing that modules bring us is also a way to organize our projects, to work on large things. And this is a law that Melvin Conway discovered a long time ago, that if you tend to organize your projects, the structure of your team might have a strong influence on how you design your project. And sometimes, if you structure your team too soon, it will impose some constraints that will make the development of your project effectively harder. So he was effectively seeing those teams and telling them, you know what? First of all, try to understand what you're doing. What are the dependencies between everything? And then later on, you can organize yourselves around those dependencies. And sometimes you need to reorganize when you learn new things. And it's not a problem, you have to do this. And having modules and really understanding the dependencies between all those modules is really going to help you do that and be more effective. Let's take a concrete example. Those people, Channable, they decided to do something that you should never do, actually. Don't try this at home. To rewrite their whole product. They were using Spark and Hadoop, and they decided, Scala and Spark, sorry, and they decided to rewrite everything in Haskell and Postgres. Wow, why would they do that? I don't know. But one very important thing that they did is that they carefully drawn out all the dependencies between all the parts of their system. to understand which ones they could redevelop, refactor, re-implement first. And that basically laid out the plan for what they had to do. And if you can minimize those dependencies, that will help you in any significant refactoring effort that you have to do. There are other very good aspects to modularity, and one of them is a very economical one, like reuse. We spend so much time writing software. I mean, it's a difficult activity. It takes lots of brain power to write the code, to specify it, to write the test, to document it, to go through all the different and weird edge cases, to polish the API, and so on. Once you've gone through the effort of having done all of this, well, you want this effort to be reused as much as you can, right? There's a great economical advantage to do this. And again, it's not only reserved for software. You find this in the industry as well. For example, the car industry understood that really well. If you took the alliance between Nissan and Renault, in year 2013, they made something like 3 billion euros of synergies. Just because you think you have a Nissan or you think you have a Renault, but inside the components, many of the components are effectively the same. And they define protocols on how those components should communicate. But they get lots of synergies of being able to define modules that are really reusable across cars. And software is, of course, a place where we do this a lot, and I mean really a lot. If you look at this presentation from Heather Miller, she was getting some statistics about the use of open source software recently. 96% of the company were using open source. And not only this, but if you compare from year to year, they are using more and more open source. And that's a huge economical gain, right? You don't have to redevelop those things over and over again. One last advantage about modularity, which is not often talked about, is it fosters, it helps with creativity a lot. If you have a system that's really modular, that's really easy to assemble, that's really easy to rewire, it helps you with any kind of experiment you want. So you can, over a weekend, take an API from here, a library from there, try to combine them and see what you get. You can run some performance tests, maybe by thinking, oh, what if I injected a cache here, there, and there, and there? And from the idea to the actual implementation, it should be super fast. And sometimes, if it's not fast, you just don't do it. It feels, I would have to change all that code. I'm not even going to try. Let's do something else. So that there's a huge opportunity cost if you don't have systems which allow you to rewire stuff and try different things, try different implementations, right? So, is that really true? Do we have any studies actually proving all of this? And there are studies showing that there are some good effects of modularity on software quality in general. Here's one of them from last year. And this study, for example, took a bunch of open source projects and evaluated how modular they were and how maintainable they were, and just drew a graph. And yes, you see effectively there's a real tendency. The more modular you are, the more maintainable you are. That's really cool, that's science, but there's also a catch. Look at that. It's only for Python projects. They did the same for Java projects, and it was not so obvious. And the reason, what they thought was the reason, is that Java is not a language that's as expressive as Python. And they said, well, when it comes to maintainability, modularity is one factor, but it might not be the only factor. Expressivity might be also very important. So that might explain. So, yes, modularity, I hope I convinced you that it's really important. It's a really nice property to have in our systems. It's going to help with many, many things. But at the same time, it's so hard to get it. It's so difficult to have real modular systems. So today I want to explore a few of the reasons why this thing is hard to get, okay? The one reason why it's hard to get is if you don't want to hear about it, if you're not preoccupied by it, if you think that's not your problem. And today, more specifically, I want to pick on functional programmers. Because I think there's a tendency when you discover functional programming to think that you have those nice functions and, well, now you can do everything with functions. Functions are the end of everything. Don't tell me about those modules. This thing was that was in the 80s. We were so wrong at that time. Functions are everything. And I think that's really wrong. And let me try to explain why. So one reason is that functions, they rarely live alone, right? Functions, they actually often come in groups of functions. They deal with the same domain. They have the same kinds of concerns. They use the same implementation. They often come as a group. And this group of functions, quite naturally forms a module. That's one thing. The second thing is that when you program only with functions, you end up with definitions like this. And I'm going to switch to Haskell for a bit, to do some promotion for Haskell. But it's the same in Scala. You can have functions like that where you want to decrypt values, and to do this, you know you need to do a bit of logging, a bit of maybe caching your results with the database, and some crypto primitive to do your decryption. And then you have your actual parameter to what you really want to do, right? And you can find this thing in Haskell or in Scala in many different formats. So either the dependencies are passed explicitly like that, or using the MTL style with typeclasses, or using the reader-t style where you extract those things from a reader, a context somewhere. But eventually it's all the same. You have some parameters to that function, and they are not totally the same. They don't play the exact same role. Some of those parameters are just dependencies. There are ways to implement your function. And when you're using them as parameters, you're doing something that is also very bad in terms of encapsulation, right? You're exposing your internal implementation to the rest of the world. So now if you don't use a database to cache your values, but you use something else, well, maybe your client is going to be impacted by this decision. But your client doesn't want to know about that. Your client just wants to decrypt values, right? You just want to go from encrypted values to decrypted values. So functions might not be the only way to structure our programs. And finally, if you look at a language like Haskell, that's like purely functional, right? It's like the language for doing functional programming. Well, there are modules anyway in Haskell. So I took some Haskell program on the web, random thing. Well, you have a module declaration on top, you have some imports, you have some exports. So there is a module system, even in a language like Haskell. So you have to wonder, where do I put my functions? Does it make sense? Why do I export? What do I import? It's actually, there is a module system. It's a primitive one, actually. It's more primitive than Scala, if you look at this. But there is one. So modularity, even if you do pure functional programming, is still a concern. End of the rant. Let's go back to our normal activity. So what else is hard? So one thing that's really classically hard, and there will be no other tools than your own brain for this, is how to deal with dependencies at large, in a large program. And the thing we're really after is this thing called high cohesion and low coupling. We want to minimize the amount of dependencies. You want to avoid that everything sees everything, because that's going to make your life really, really hard. And that thing is difficult. Some symptoms of this that you might find is something that you can call the butterfly effect, where you have one component in the middle that everyone depends on. And possibly that component also depends on many things. And this makes your system very, very unstable. So sometimes you can call this the utils effect. Let's just put everything in that util package, it's fine. So it's really a butterfly in the sense where you have weather systems, where they say that a butterfly in Singapore flapping its wings because it's a chaotic system could trigger a tornado 3 weeks later in Kansas. It's a bit like that. It can have a devastating effect. And dependencies are not totally obvious. Some of them are kind of obvious. You do an import, well, you have a dependency on the name. But some of them are more subtle. You can have some dependencies across time. Something will work only if something else has been done before. That's typically the case when you have like side effects. Sometimes you have dependencies on your data. Someone had the brilliant idea to codify that the MasterCard 999999 will be for a test customer. How do I know about this? Well, you have to discover it, right? It's like implicit knowledge that is passed around. So this is a presentation that was done at Yale, and there's a website called connaissance.io where people listed a bunch of ways that two pieces of software can have some interaction even at distance because they have to know things about each other. And there are many ways in way where two pieces of software can effectively be related to each other. And this leads then to using some laws like the law of Demeter, where you say, well, maybe this piece of code has too many dependencies because the car here has to know that the throttle can accelerate. Maybe it doesn't have to know that. Maybe you just want to see that the car can speed up, and that should be its only concern. So Demeter, for example, was a project where they tried to push this principle to the maximum. Never have transitive dependencies like that across all their layers. So yeah, finding out those dependencies, and especially all the hidden ones, can be really difficult. But it's not over. Even if you have nice components, if you understand your dependencies, well, the whole behavior of your system will still be kind of an emerging property. Because you can have many paths across how all your components are used and around all the interactions they can have together. So that makes also modularity hard, because it can be still hard to understand, okay, can I split this one into two other ones? What are going to be the exact effects of doing this? Not obvious. And it's especially not obvious if we lack specifications. And I think as an industry, we are still very poor at specifying what we do. Most of the time, sometimes we have tests, and that's good. We need tests and more tests, and properties tests, even better. Properties tests with coverage, even better. But in many places, we should have things that are more like formal specifications. And this is an example of a tool called TLA+. And TLA+ is the language, which is really good for concurrency. So that's the moment where we should reach out for those tools when we have complex problems like that, because they will give us much more confidence that the API we're providing is actually sound. That's difficult. So dependencies, finding out the right components, having specifications, some documentations for them, already hard. But even if you have this, those components, they will have to communicate with each other. They will have to exchange some form of data with each other. And data is terrible. Data is like the ultimate butterfly, because it's used everywhere. So at the moment where you define a data model for what you're doing, it's likely to be a dependency of everything. You will end up having that thing everywhere. And sometimes it's even worse, because not only you have one data model, but if that data model was sent somewhere else, was serialized, was saved to a database, whatever, you not only depend on your current data model, but possibly on older versions of your data model. And you have to deal with that. It's even harder to remove, unplug, separate. It's difficult. Let's take a silly example. But I like this one. It's a new proposal for a calendar. What if we had months in a year where every month had the exact same number of days? Everything will be super regular. I wouldn't have to use my hands like this to remember if it's 31 or 13, right? Super easy. Great, and the last day of the year is a vacation for everyone. I love it. But can you imagine replacing this system everywhere, in all the IT systems of the world? What would be the cost of that? It's impossible. It would be huge for no obvious advantage. Data is really everywhere. And changing data and extending data is really hard. So this is the kind of illustration you have for the expression problem. So raise your hand if you know about the expression problem. Cool, lots of people. So the people who don't know about the expression program, you fetch someone who knows about it, and then you will make new friends, okay? I'll explain. But most of the time, the expression program is explained in a small scale, right? I'm creating a small lambda calculus language or arithmetic language, and I show you the expression program. But this thing happens at larger scales as well. Like, this is the model I had when I was working at Zalando. Zalando is selling shoes and clothes, and the data model is like, you have a shoe, that's the model, and different configurations, one for each color, and for each configuration you have different sizes. That's all cool. I mean, you can grow a full company based on that. It's nice. But then there's a point where you want to extend this. You want to have more information about fashion blogs. Okay, who is talking about my shoe? And you want maybe to sell other things like beauty products, cosmetics. Where can you fit those cosmetics inside this data model? And the problem was so hard that they decided to throw everything away. Let's start from scratch, from a different data model. And up to this day, the migration is still going on. It's a huge effort. It's like rebuilding your whole data system. I mean, that really shows that data is not a modular thing. It's not something that you can opt out really easily. That's difficult. Another thing that's kind of painful for functional programmers. So we spend so much time in our programs trying to avoid side effects. So in the small, it's nice. No more side effects. We can compose things nicely. It's all good. But at the system level, we have lots of side effects. We still put things in the database, and we have all those interfaces that just return unit because, well, I'm just sending stuff. I don't know what happens. And so at the system level, we have all sorts of time dependencies, things that need to happen before I can do anything. My schema must be migrated before I can even use it. How do I know it's been migrated? I don't know, just try. That's a problem. Something which is not really recognized as a problem, but I feel it's a real one, that I would like people to work on this, is once you have all those components, you know their dependency, you know what they are doing, we don't have an easy way or very standardized way or like some formal foundation for thinking of how to assemble those things. Every time we assemble components, it's very ad hoc. And we have needs for different ways of assembling stuff. I mean, if you have a graph with different components, you might want to say, oh, I want to replace this one on the top. That's probably easy. I want to split this one into two. That's probably harder to define, even just to express it. I want to replace now all the components that have this type with a different implementation. Well, how do you describe this? And we don't have this language, right? And I think this shows in some very concrete examples, and one of them is build tools. So personally, I would hate to be an author of a build tool, because people are never happy with build tools. You cannot satisfy anyone on the planet with build tools. No one likes build tools. And I mean, it's hard to create a build tool. Where's John? I don't know where he is, but good luck, John. And I mean, one of the reasons, there are many reasons, but one of them is that there's lots of configuration that's needed. And very often this configuration is in the form of a graph with dependencies. And this is a presentation from Chris Vogt when he was showing CBT, a build tool for Scala. So he says, oh, you have your main graph, and you want to say, oh, I want that graph to be also working for Scala 2.11 and also for Scala 2.12. So he's effectively using the host language, which is Scala in that case, to override some stuff. So he's using something that was not designed for graph manipulation, which is inheritance and overriding mechanism, to do those graph manipulations. And this works well in that case. But in other cases, well, it's more complicated. You have to extract a module, do stuff locally, re-inject stuff. Of course, it's more complicated because graph manipulation needs a language that it just doesn't have. So many obstacles. One of them is incredible. How can you in the world produce components that are reused if the rules are changing all the time? I mean, I started with this. J2E was like the way to produce enterprise components that would be reused forever. Where are those components right now? They don't exist anymore, right? And because in the meantime, the web arrived, right? The web, but the web was also reinvented again. You had to change your techno again. And then you had things like different ways of storing your data, of accessing it. And you have, wow, big data as well. And if you look on the languages side, it's all over the place, so many languages. So every time you have a new language, well, nice, new capabilities, but you have to reinvent a full ecosystem, a new functional library. And while ZIO might be super great, well, at the moment, you're rebuilding a full ecosystem around ZIO instead of maybe just building apps. It's kind of a shame in a way, right? That you have to rebuild the world all the time. But don't mistake me. I still like it. I think there's good progress. I think we're doing very good stuff, enabled by things like Docker and GitHub. It's good, but it's also a shame that we cannot reuse as much as we want to. And the worst is that many of the assumptions we have right now are still going to break, and we will have to rebuild things all over again. So right now we are at the period of maybe, I don't know, 10, 15 years where we started using more and more cores. So asynchronous programming began to be a real thing. I mean, these days you cannot create a testing library without embracing asynchronous programming inside your library. I mean, when I started with Specs 2, there was no such thing really as asynchronous programming. It did not really make sense. But now it has to be baked in really. And we are still at the end of this cycle, but other things are going to happen. This paper shows that now in some data centers, I/O is faster than CPU. And we've been told repeatedly that, oh, well, I/O is super slow. You need to be careful with your I/O operations. It's not the case anymore. So the systems we are dealing with are going to evolve to give you this kind of advantage, to take advantage of this super fast I/O now. And that means, again, maybe that will have some impact on your HTTP libraries, your I/O libraries, and so on. And again, you will have to adapt to that and change your components. So, I mean, those are a bunch of reasons why modularity in the small, modularity in the large is difficult. I'm sure you can come up with plenty of other reasons on your own to understand why this thing is difficult, right? So, where do we go with this? What can we do? What kind of hope we have? What's with this? And I think before we have a look at all the tools that we have at our disposal right now, it's good to go back a bit and have a look at what was there, where were we coming from in terms of languages and concepts. So I'm not exploring the full field, and I don't promise that all the dates are correct, but let's have a look. So if you look at the 60s, a language like Algo was introducing procedures, and at the time something called like structured programming. And it was already a good step, in the right direction, trying to encapsulate more and more complex behavior with some kind of logical abstraction. And the funny thing is that if you hear some complaints of people at the time, they thought that this would not work. Some people said, no, well, it will never work, mate. You will have to program in assembly at some stage. That's not going to work. But eventually we made it work. You very rarely have to program assembly these days. You have higher level abstractions that are nicely encapsulating small concerns that you don't have to worry about. Who knows when objects have been invented? Well, not so late after Algo, 67. And I want to mention this because objects were not invented for reuse. That was not the primary goal for objects. The idea with objects was to be able to simulate dynamic systems, to see how agents were interacting with each other, try to see how things were progressing and what kind of messages were exchanged and so on. So the idea behind objects was totally not to reuse things, to really make modules. Maybe the first step for modules was with a language like Modularity. Well, it has module in the name. And it was really the recognition that how you start writing programs that are larger and larger and larger, it's good to start separating concerns, having namespaces, limiting the visibility of some of the things where you say, I know I can export this, on all the rest should be private, that's my own concern, I know I can import that and so on. And Modularity was the first language to invent the dot notation, right? When you can qualify a function or procedure with the module it comes from. So that's for modularity in the large. At around the same time, a language like Ada was doing modularity in the small. How do you encapsulate small differences into the implementation of a user data type, for example? So you want to work with years that represent years. You don't really want to know that they are internally encoded as integers, right? And being able to hide that fact and just program with years, months, and days gives you a lot more flexibility and a lot more isolation from any kind of other implementation that you might come up with later on, using a different ways of encoding this same information. So again, you have this idea of having an interface and a different implementation, and the interface being just at the right level of abstraction that you want. And along the same line came like the golden standard for modules in '84. It was like 25 years ago. And it had already had lots of tools for modularity. So of course this idea of having an interface called a signature here, but it's already very rich because you can have type members, right? 25 years ago. Something that I discovered while preparing this talk, you can declare that this module can throw an exception, but not for each function, just at the level of the module. You globally declare that this thing can throw this type of exception. And then you can have implementations where you specify the implementation of all the methods, you are more concrete with the types, how you implement your queue, and so on. So this, and also the fact that you can parameterize modules with other modules, already gave people lots and lots of ways to structure large programs and to depend on interfaces and not depend on implementation and have stable systems. That was great, right? Unfortunately, around the same time, we started needing more software, like a lot more software. So we started just producing software and using whatever was at our disposal to do so. So, well, OO seemed to be not such a bad idea, so let's try OO, however we can. Maybe there's some good stuff in there. So let's try things like multiple inheritance. And that's complicated, actually, because you have this famous diamond problem with multiple inheritance. So maybe let's not do that. Let's do, well, single inheritance. But actually, even this one can be complicated. You can have like a child class using some behavior defined in a parent class. Okay, why not? It has access to it. But then the parent class itself can have its own behavior, have some holes for having things specified in child classes. How? And now you have this kind of double dependency between those children and parents. And if you are not careful with that, you have those dependencies sometimes on different levels. And your whole hierarchy of classes becomes very bloated and effectively not modular at all, because everything starts depending on everything. You touch one class, you break the parent, you break some children, it's a mess. That's difficult. So people tried other things, and recognizing that some things were really issues that needed solving. One of them was tracing. How do you trace the execution of your program in some kind of generic way that's not boring, that's not too boilerplate? Let's try to use annotations for that, and something called aspect-oriented programming, where we put some aspects that are kind of transversal for tracing, for transaction management, things like this. This thing is also very fragile. The definition of the point cut here is using a string with some kind of regular expression. So every time you refactor your code, the string is not refactored, so you can potentially break everything again. And it's also using a form of metaprogramming, which requires other tools in addition to your regular compiler to work. So people tried to use that, and it was too complex and too fragile. But we tried other things, like, EGBs. If objects are so good, we should double down on objects. They should do more. They should be able to persist themselves. It should be able to remote themselves. You should be able to call them from anywhere. And I mean, I've been on such a project, and it's been a nightmare. Super low productivity. You had to declare XML files for everything. Super low performance. It was a real nightmare. Who's been on such a project? Who survived? Oh, so many survived. Okay, so then what was the response of the community? Well, maybe let's go back to normal Java objects, right? Plain old Java objects with just a few annotations to know how to wire them. And again, recognizing a real problem. How do you wire large applications? This is a real problem. We need a language for this. Well, maybe annotations are the way to do it. Well, again, if annotations are so good, we should use more of them. And then you have so many annotations. You don't really know how they compose, what they do, how they interact. Sometimes they are using some strings for their specifications. It's fragile. Where's the interface? Oh, it's there. So, again, every time you use too much metaprogramming, maybe there's a problem in how you're approaching the problem. Well, and in the realm of metaprogramming and having all sorts of flexibility, you have monkey patching and all those dynamic languages. They are super cool, they are super flexible. You can, in a very small amount of code, describe so many behaviors. But it's very fragile, it's very easy to break, it's not so easy to understand. You don't know when the behaviors are being injected, removed, re-added back again. It's terrible. We've had some very bad experiences with that. So, wow, we had some good things in the past. We had the impression that the history was going in one way, and then we had like some failed experiments. So where do we go from there? Where do you have other ideas? Right now we have better tools also. We know a lot more about functional programming, about typeclasses, about all those things. Should we use them, and how should we use them? And I think we should be also careful with that, right? We should use those abstractions as we need them. Some of them have a cost, right? So let's be careful. And possibly let's start with getting our priorities right. And one of them, when we design large systems, is really getting the dependencies right. This is still a difficult exercise. But the tools we have for this are still the same. A good old division between an interface and an implementation, right? So trying to make our interfaces as abstract or as domain-oriented as we think they should be, and then find the nice and clever ways to implement those interfaces. And how do we find those components? Well, maybe we should go back to the oldie but goldie articles describing those things. And so there's a study from the 70s showing two different ways of decomposing the same system. Very simple one, but those two different ways. And one way is effectively more fragile than the other. And David Parnas said, okay, the way that's more stable is when you try to encapsulate as many design decisions as you can behind those interfaces. You should hide those difficult design decisions behind those interfaces. So when you need to change how something is implemented, how it's represented, whatever, you know you're not going to impact the rest of your system. It's easier said than done, but that's really the effort we need to make. The other thing in that space about this utils problem is that most of the time we're really obsessed with what we're doing on our project because we're working on, I don't know, a travel agency, on having a website for poker games, and that's our main concern. And okay, that's important to focus on that domain. But in the course of developing that, we developed some very useful utilities for dealing with HTTP, XML, text, whatever. So at this stage, we should really resist the temptation to put everything into the same bag. So when I create a new text function to do some useful text manipulations, well, I can take a different hat and put a domain design-driven hat on my head and say, now I am a text library author, and I should be the best text library I can, even if it just lives inside my own huge project. But the thing I'm working on right now is just text. I'm not concerned with the travel agency problems. So and try to separate as much as we can all those domains, even if they are very small. The next thing we can do, and it helps to understand how things are going on at large scale, is try to visualize our dependencies. This is not something I see done all the time, but that really helps to see, okay, what are my real dependencies? Do I have to read all the code line by line to really understand how are things connected to each other? And sometimes I'm missing some very obvious dependencies that should not be there. So trying to represent them can just help us identify those things that should not be there, and that we can break into and invert the dependencies, and there are all sorts of tricks to change that graph. Once we have those components, I think it's always good to take the time to think about them one by one as if they were like some very nice products that almost you wanted to sell on its own. So just take the time, like 2 hours, to say, is it well documented? Does the API look nice? Does it have enough tests? Are they covering what they should cover? Is it well explained? And all of this. Do I have all the edge cases covered and all of that? Is it at the right place with all my other modules in the right namespace and so on? So, I mean, those are just, in a way, rule of thumbs. It's just by doing, trying, sometimes reverting some decisions that we can arrive at something that has just the right amount of dependencies. It's hard work. But then, when we have those components, and it's been more and more apparent with the adoption of functional programming, nowadays we have more options on how to implement those components, how to structure them. And I want to talk a bit about those libraries and those approaches for modularity and how to deal with effects, right? And we have many options. And I mean, for someone that's new to functional programming, new to Haskell, new to Scala, this can be very hard to know, okay, what should I use? So like monad transformers were indeed an approach to modularity. And it says in the title, it says, oh, it's about modular interpreters. You have then algebraic effects and all these effect libraries composing effects together into a super monad that gives you access to many things that you can have at the same time. And you have this typeless final thing, which I think is not what we talk about when we talk about it in Scala, but it's more about partial evaluation, but maybe it's a way to structure our applications. And from the Haskell world, we have the reader T pattern, which you can see maybe ZIO as being somehow following that pattern. So how are all these things different? Are they the same? Are they fundamentally different? It's not easy to really see if they are different or really just the same. Because on the surface, sometimes they look really like they are the same. They are just more like syntactic differences about, am I using typeclasses? Am I using effects that I'm passing as constraints? Am I using a context where I'm extracting some capabilities using a reader or some implicit function in Scala 3? It looks more or less the same. So I think there are some important differences. And I'm giving you like 2 pointers to think about those libraries. The first one is, do they enable generalized recursive expressions? And I will explain what it is. The second one is, how easy it is to work with those libraries to make sure you preserve encapsulation and to make sure you can wire and rewire things as you want. So let's see the first thing. If you look at the tagless final paper, it shows a language that's a bit like that, where you can build arithmetic expressions that depend on each other, that are kind of recursive. The f parameter is recursive, right? You can add two f's together to get a new f. And they show how you can extend this language with more constructs like this. And this gives you actually some huge power, because that means you can build large expressions that can weave into different concerns at the same time and have different ways of interpreting those concerns. This is huge. You can implement things like coroutines with this, non-determinism, bracketing. You can do lots of interesting things. But it's also very complex, those effect libraries, and I'm very guilty of having produced one in Scala, and I totally apologize for that, but I did it. And those libraries are really complex at the heart. This is a message left by the one author from one of the Haskell libraries. So, whoa, depending on the effect, they can have some strange interactions, and it's not totally obvious how they should interact. So those libraries are definitely worth investigating, but unless you have some large rewrite needs in your application, I would not advise you to use them. And if I can do a rant, please, if you say the word tagless final, just read the original paper. Because when we say tagless final in Scala blog post, most of the time it's an interface that's parameterized by a type constructor. It's not really what the original paper was about. So take this opportunity to read the original paper. That's worth it. Yes, encapsulation. One thing that you need to make sure you have when you use any of those libraries or any of those approaches is that if you think of your dependencies, of your graph dependencies, you need to make sure that one node doesn't see the other nodes that are used by the node just below, right? You should only depend on the interface of something, and you should never see its implementation. That's like the golden rule, right? If you don't have this, if you expose too much of the internal implementation, if you call a function that tells you what it's doing internally, you're probably doing it wrong. The other thing is how easy it is to wire and rewire your application. And in that space, there are many solutions. So you can find like just manual wiring, use of typeclasses because the compiler is doing some wiring for you, use of effects, sometimes macros or implicit in general, mixing traits together. We use all sorts of mechanisms to do this, but they don't have the full power. They don't have always the full power to help you wire things as you want. They all come with trade-offs. So for example, if you take the reader-T pattern as exposed in the Haskell blog post showing this pattern, you will see that it only allows you to replace low-level dependencies, like a logger, like a connection to something. And as soon as you want to replace larger parts of your graph, well, it's not as easy, because the larger parts are going to depend on smaller parts. So effectively, to be able to replace a larger part, well, you have to build it yourself to be able to replace it. When coming here, I was thinking, well, what about ZIO in that context? I wonder, which spectrum does it fall? And I think it's kind of complicated, because ZIO is kind of a mix. It's using both a reader-T through its environment, but it's also using traits composition when you see the module pattern, right? When you use the module pattern with ZIO, you're effectively using one capability offered by the Scala language, which is to have mixing composition by mixing elements of traits together. And that's quite cool. I mean, that gives you some capabilities. But that's not also not giving you everything. There are some things that you cannot do. That also means that in your graph of dependencies, when you have like the newsletter, depending on the postman, it can only ever depend on one postman. You cannot say, in one part of my graph, I want to use this postman. In the other part of my graph, I want to use another postman. Because, by the way, things are composed in trait composition, it has to be the same instance, postman, right? You can probably work around that, but it necessitates more work to do. It's not that obvious. And, well, also this pattern comes with boilerplate. So, well, macros were proposed to help with this. But again, I'm using macros. Maybe I'm doing something wrong. Why do I have to use macros? And it also doesn't solve all the problems, because you have things like, some things are very effectful when you instantiate them. So for example, if you need a connection to your database, not only you need to mix in those traits together and have those components declared and those traits and things in objects and interfaces and so on. But you need on the outside to have created your connection first and then pass it to your trait mixing. So you effectively have a building process that is like staged into, in a way, different phases, right? It's kind of complicated to me. Honestly, it feels more complicated than it should be. So if you want to know more about what I really think about wiring, you can have a look at this Haskell project. I won't talk about it today. That's really cool. So what is my advice to some people coming fresh to Scala or to Haskell? Is first of all, I don't think the reader pattern is a good one, personally, because it exposes, fundamentally exposes dependencies. So you call a function, but as the client of the function, you have to pass things that the implementation is going to need. And that's really cool, because you can change this implementation for testing. So for testing, it's great. But for using, it's not so great. So we should encourage a way of building the applications where you have really two distinct phases. One phase where you build stuff, and one phase where you just use stuff, right? So those dependencies, they should be stashed away. And if you look at functional programming, conceptually, we have this tool. This is called partial evaluation, right? You have a function, you start, you give it some arguments, and then you have another function where people don't see the arguments anymore, but they can just use it. It's really cool. You do your wiring in one step, and then you can use everything. That's nice. And then you can just use this. And how do we do this in Scala? Well, one very simple way is to have traits and case classes. Well, you have a case class, you pass in your constructor all your dependencies, and your case class is effectively implementing methods. And the methods, they don't show what they are using. It's encapsulated, it's hidden. No one has to know that you're using a logger, that you're using a database. And then at the beginning of your application, well, now you are free to make some side effects to create your database connection, to push the logger where it needs to be, to push your database for the components that need your database, and so on. I think it's a very simple thing to do. That's something that people who are new to Scala everyone should understand this. It's a very easy way to build applications. No DI, no MTL, no words like tagless final, I don't know what that means. No effect libraries that use the type system in so many ways. It's so easy, I should probably market this and sell this, right? It's powerful. But not so fast. Of course, there are some trade-offs in many things that we do. One trade-off is that, well, I said, all the wiring is manual. And that can be boring. And if you have a large application, that can be some boilerplate that you don't want to have if you want to rewire your application for different contexts, for different kinds of tests, for example. Maybe you have to abstract also over that phase of wiring your application. But there are other issues. One of them is that those components, just using traits, sometimes are too simple. Sometimes, if you take a component like that for SQL, that's kind of encapsulating a library for accessing Postgres, for example, this is kind of a leaky component. Because I bet that the query type or the two-row data type class can actually only be used with that implementation. It's probably not usable with another implementation. So this interface looks good, but it's actually very leaky. And it's also not solving all the problems. One very common problem that we have in applications is pass a request ID from call to call, right? And you cannot have one component that's going to provide a request ID for all the calls, right? Because you can have many different calls happening at the same time in your system. So essentially, things like request IDs or transaction context, they have to be given through a reader pattern. It has to be given every time you call something. You need to tell the components you're using in what kind of context you are, and that thing has to propagate it. That's unfortunate, but that's how you stay functional. Yeah, that's the end of my rant on those libraries and how you should use them, and probably start simple before trying to use more elaborate techniques. And then we have so many other tools that we know and love about how to build systems that are really compositional and really modular. So for example, we know that having variables and for loops and printlns is not the right way to do it, and we are much better off having streams and being able to have a stream of elements and add a new operation on top of it and do some maps and filters and fold over that stream and get some more information just by adding more code on top of existing code, which is a good criteria for modularity. Every time you find yourself thinking, oh, I want to implement this feature, how do I do it? And you say, oh, I can add this code here. I don't have to modify anything else. That's a win. It's fantastic. You should cheer up. You should say, I did my work right. The other thing is about streaming stuff. So we still have databases everywhere. But more and more people are trying to get rid of databases. And you should see if it's not possible in whatever you're doing to do the same thing. So that's a blog post by Martin Kleppmann showing how it's possible to turn the database inside out and transform databases into streams of data, where you just recompute things and cache things as you need them, but effectively you can use functional programming to do these things. Unfortunately, up to recently, it was not possible to do everything you do with a database. In particular, atomicity was a problem. If you had two independent streams, it was hard to ensure atomicity of two different operations. But the people doing the Flink library came up, apparently I haven't investigated that in detail, with a way to do ACID transactions over stream processing. So maybe now there are also ways to be functional also at the system level. And that's also a very good way to get more modularity, because we can have more stateless programming, we can have more, all the goodness we have with stream programming in the small, we can have it in the large. What else do we have that's super useful? Well, types. Types are great. They are a great way to ensure modularity. We've been knowing that for a long time, right? Using collections and generics. You don't want to re-implement the same collection for different types all over again. But more generally, every time you can stick a type parameter somewhere, you get modularity. That means, well, you can put whatever you want, I don't care, I will do my job as specified. It's already a win, all the time. That's great. And sometimes, well, you cannot work with any T. You can only work with things with some constraints, so you use typeclasses. And this is also another way to get modularity. So, for example, recently at work, we started migrating from communicating using JSON to communicating using message pack. But that was super easy. That transition was super easy to do. It was very localized. Each data type had to specify a message pack instance, and we were done. Thanks to type classes. Wonderful. And there are other techniques coming up, like hierarchy in data, for example, where you have like a person class. But sometimes the person class comes with things like, oh, we have options for the name and the age because those things need to be validated. Or sometimes you can have the history of all the names and all the ages. And well, you can generalize on top of the shape of your data. And people are trying to find ways to work with data that is kind of more modular in terms of the effects it can have. And with hierarchy data, you can do things like a general validation. You can transform some data of maybe into maybe of data. And this can be done generically. You don't need to know what is your data. It can be person, it can be house, it can be whatever. It's possible to write a generic validate function that is always going to do the right thing. That's really cool. And what else do we have? But coming probably later on. One very thing was something which I find very interesting because it's solving a very difficult modularity problem for some systems. Something called variational typing. In a system like BusyBox, it's a system that provides people with Unix utilities for embedded environments. But those environments are so different that they need all sorts of tweaks for those functions and ways they interact with the rest of the world, and it's really hard. So they have many, many configuration options. Changing the code, effectively changing the code. The code is not the same, it's just not if then else. It's like, if you have this option, the code is totally different. The question is, how can you make sure that with all those combinations, the code even means anything? Does it even compile if you change your configuration options? So people start working on type systems to deal with this thing. And to take another concrete example, more recently, the Haskell community is looking at this to change the if-defs that there is in some Haskell libraries where you want to say, oh, if I'm using GHC7, I should write the code like this because Monad was implemented like that. If I'm using now GHC8, it should be like this. If I'm using the base library 4.2, it should be like that, otherwise it should be like this. And you have all those combinations. It's actually possible to have a compiler that's going to ensure that even with all those combinations, your code will still be valid, will still do the right thing. So that's something to keep an eye on. And the other thing is that there is still some research on modules. I mean, we haven't finished writing the history of what modules should be, how can we use them, how can we use them to structure large systems and so on. So this is a PhD that started this year about trying to integrate modules into dependently typed languages, because there are some strong interactions, and that person says, oh, a type class, a trait, a record, a module is more or less the same thing. If you add lows into there, it's more or less the same thing. So he's trying to explore that. There's also this thesis trying to explore what it would mean to unify in the ML languages the core language and the module language. Because if you look at the language like SML or OCaml, those two languages are effectively different languages. They don't have the same capabilities. You cannot do the same thing. Two different languages. Can we unify them into just one? This is what 1ML is attempting to do. And finally, if I can direct you to just one paper to read, is a thesis by Scott Kilpatrick, and it was just out like last week. It's very recent. But the introduction is really good. It shows some of the problems that you have with modules. It introduces some terminology on how to talk about modules in the large, in the small, with things like strong modularity or weak modularity. And the purpose of that thesis is very practical, is how can we take a language like Haskell and retrofit a module system on top of it? Is that even possible? And this is the foundation for something called Backpack in Haskell. But the introduction is really good because it explains all sorts of challenges related to having modules in large systems. So, today I hope I convinced you that we should care deeply about modules, about trying to make our code as modular as we can, even if it's hard, even if it's difficult, even if it takes several trials and refactorings to eventually get it right once we really understand what that thing should be doing. But it's really worth thinking hard about that. And we have tools at our disposal, like old tools, interfaces and implementation, very old tool. And we also have new tools, right? Like functional programming and types, and we should use them as much as we can. So yeah, that's it for today. I hope you really have the will to come back to your work and use those Legos with joy.